today. Rad has done really fascinating work in multiple areas, including his really cool work on Bernoulli factories and series of working on algorithms. Today is going to talk about when matching meets patching.
All right. Thank you, Paulo, for the introduction, and thanks everyone for coming to my talk. And thanks to both of you for having us here. It feels great to always give a talk at Science Institute. So today I'm going to talk about when matching meets batching and how to design optimal multi-stage allocation and matching algorithms and some of the applications that these techniques have. Before jumping into my talk, I just wanted to say that this is based on a series of joint work with my collaborator, Yiding Feng, who is currently a postdoc at Microsoft Research in New England. Yiding is on the job market this year, and he's fantastic. Wanted to spend 30 seconds advertising him. So if you have jobs, he's looking for jobs. All right, so I've designed the talk so that the talk is kind of a high-level mixture of high-level ideas and technical details. So whichever tribe you belong to, whether you're here to learn about the model and the algorithm, or you really want to learn some of the algorithmic constructs that we have in this series of work, hopefully the talk has something to offer. With that introduction, let me jump directly to my talk. So this talk is really about matching supply with demand, which is arguably one of the most classic problems that has been studied both in CS, economics, and operations. And in particular, what I'm going to look at is the scenario where decision maker is dynamically matching demand, aka service requests, to supply, aka service providers. And with the advent of online marketplaces and platforms, this paradigm has become a central operational task. To just name a few applications, maybe it might be a little bit boring for this audience. For example, in a sponsored search, you have to match search queries to advertisers that are willing to show their ads to their users. In video YouTube advertising, for example, impressions from users should be allocated to advertisers. In ride sharing, ride requests should be allocated to drivers. In cloud computing platforms, such as AWS, jobs should be matched to servers. In online food delivery, we have orders that should be matched to couriers. Online retail, we have all sorts of delivery requests that should be matched to internal fulfillment centers run by the retailer. And finally, this is kind of a cool modern application. In digital freight network, shipping requests should be matched to carriers that are willing to do these jobs. So maybe I can spend an hour talking about each of these applications, but definitely is not what I'm planning to do. Instead, I'm going to look at one aspect of these applications, which makes them quite different, and that's the allowance for latency. So what does that mean? Suppose the demand request arrives. How long you can keep the demand waiting until you match it to a supply? And when you think about this allowance for latency, these applications have quite different amount of allowance. For example, in a sponsored search, things are almost immediate. When the search query arrives, you have to match it to an advertiser immediately. Having said that, I heard from a colleague at Google when I was there that ad decisions at the bottom of the page are not finalized until the user scrolls down all the way to the bottom of the page. And that gives a window for Google to optimize the ad allocation decision. But yeah, good. Let's take it like that. All right. But here there are some other applications that there is actually natural allowance for latency. For example, in YouTube, most of the ads are displayed maybe after a few seconds when you start watching the video. The user comes, start watching a video session, and then 10 seconds after, there will be the first ad that will be displayed. So if you look at the interval of length 10 seconds, there will be a lot of users that the video has already started, and therefore the platform can pull those requests and make same allocation decision for all of them. And then in ride sharing and maybe in cloud computing, the things is a little bit more relaxed. For example, if I have a job that needs to be done on one of the AWS virtual machines, maybe I can wait for another 2 minutes. In online food delivery, still it's very relaxed. If you wait for your food for another 10 minutes, it's fine. And if, for example, Amazon can add 1 day to its delivery time so that it makes this operation way more profitable, maybe this is something that the company might consider. The point is, in all these applications, when there is an allowance for latency, whether it is organic or it's deliberately induced by the platform, they can do batching. So what does batching mean? Imagine the demand requests are arriving over time. The platform, by introducing waiting times, are going to group these demand requests together. Each group is called a batch. And then at the end of arrival of a batch, is going to make what I call a stage-wise decision for all the demand requests that are within that batch. So this is in contrast to what we usually know as online decision-making, where you make an on-fly decision for a demand request the moment that the demand arrives. So here you wait until you have a batch, and then you make a stage-wise decision, one for each batch. As I said, in some applications like YouTube video advertising, there is this organic delay, and therefore you automatically have these batches exogenously kind of given to the platform. In some applications, such as ride sharing, the platform induces this batching. So this is from Uber's website, Uber Marketplace website. On the left side, you see the matching as you go algorithm. On the right side, this is what they really do, which is the batch matching practice. So a rider arrives, you can either immediately match the rider to the closest driver, or you can wait a little bit, start doing the batching until the market is thick enough, and then you do the best matching given the pool of the riders that you have. All right. So definitely this comes at a cost, and that's keeping the rider waiting. But still, if this is something that is acceptable, you can, as a platform, you can benefit and make a better matching decision. So why batching is helpful? It's a very simple question. In fact, as you pull the request, the market becomes thicker. And therefore, as a platform, we can make more anticipatory decisions by essentially bringing future into the current decision. But I want to also argue that not only it is helpful for making more efficient allocation decisions, it has other operational benefits. For example, Amazon has reported that they could reduce their waste by batching the delivery requests together, simply because there will be less number of packages they need to send out to their dispatching centers. And in this way, not only you can make the allocation more efficient, you can also reduce other, what I call operational costs. For example, in this case, waste. However, trivially, it comes at the cost, and that's the latency. So it's really important to understand the actual trade-off that you get between batching and inefficiency. So what do I mean by that? As you have more number of batches of smaller sizes, definitely you get closer and closer to the online decision-making, and therefore there will be more inefficiency in your allocation decision. To just see two extremes, if you look at one extreme and you have one gigantic batch that has all the demand requests, then you are going to make one allocation decision for the entire sequence, and that gives you the best matching you can hope for, the in hindsight optimal matching. What other metric you want to target? On the other extreme case, you have one single vertex in each batch, and that will be the case that we call online decision making. Right? Still, this is going to be sort of efficient, but definitely not as efficient as the in hindsight optimal benchmark. And here's the question I'm trying to address. What would happen in the middle ground regime when you have some limited number of batches? In particular, given a fixed number of batches, can we really characterize the efficiency performance of multi-stage matching or allocation algorithms? So this is the informal question I'm going to address in this talk. And sometimes I have been asked this question, how do you do the batching? This is not what we addressed in this talk. I assume that the batches are given exogenously. And the question is from the algorithmic perspective, how the algorithm designer is going to improve the algorithm to make the allocation decision better, given the batches that are arriving over time. Yeah.
Would you like to make an acceptance revision decision?
No. So basically, that's the point, right? So you basically have a batch of the people that arrive.
You don't have to commit, right?
For the batch, I'm going to commit, but
no, but when they arrive, you don't.
Right, but you can think, what is this? This is just a perspective. They have they have arrived in an online fashion. You kept the first person waiting until the end of the batch.
Just commit something.
Yeah. Or another way of thinking about it, maybe it's easier just have a bunch of nodes that arrive at the time. The moment they arrive, you have to make a matching decision for all of them at the same time. And these are irrelevant. Let me try to formalize the problem I'm going to solve in this talk by revisiting some classic models in online packing linear programming. Maybe again, for this crowd, I don't need to explain a lot, but let me do it anyway. Imagine you have an instance of a packing LP where the packing constraints are already there, so they're given offline. And then you have LP variables that are arriving over time. That's the online aspect. Maybe one canonical example of this sort is the seminal work of Karp, Vazirani, and Vazirani, online bipartite matching, which is basically the following problem. We have a bipartite graph G between two sides, the supply side, the offline side denoted by V, the demand side, the online side denoted by U. The demand nodes arrive over time. Once a vertex arrives, it's going to reveal the incident edges to the offline side. And now the goal of the online decision maker is to make a matching decision, basically to which available offline vertex match this arriving online node, so as to maximize the size of the matching at the end. And the goal is really coming up with a matching that is as close as the in hindsight optimal matching, which is the maximum matching when you know the entire graph. There are other variants of this sort of online bipartite allocation that has been studied in the literature. For example, I can mention the vertex-weighted B matching, in which you have a capacity on each offline node. Let's say Bj, and each offline node comes with a score weight, and the goal is to find the online matching that maximizes total weight at the end. There is also online budgeted allocation, also known as the adverse problem, where basically you have search queries arriving over time. You have advertisers with a given budget. Once the search query arrives, all the advertisers are revealing the bids that they have for that search query, and the goal is to allocate the search queries to advertisers so as to maximize the total collected bid while you're respecting advertisers' budgets. There are also other variations. Some people in the audience have worked on those. For example, edge-weighted matching with free disposal, whole page optimization, or configuration allocation, online assortment, so on and so forth. But they are all derivatives of this very basic model. For the purpose of this talk, I'm going to focus on vertex-weighted B matching. In particular, I'm assuming that the capacity is equal to 1. And I'm also going to only look at fractional matching. Basically, the algorithm can make fractional solutions. You can think of the large budget version where the algorithm is forced to make integral allocations, and then there are standard independent randomized rounding together with concentration bounds that can give you the same results, almost the same results for the large budget. But for the purpose of this talk, I'm just going to look at the capacity 1 and fractional matching. So this literature was really about online allocation. So we are going to diverge by assuming a new mode of arrival, which is what I call the batch arrival. We have k stages. As at each stage, a new batch consists of a bunch of demand nodes that arrive and reveal their incidence edges to the offline set. For example, if k is equal to 2, this is going to be the first batch. They arrive, you see the edges. Then there is the second batch. They arrive, you see the edges. K is equal to 4. We will have 4 arrivals. I make no assumption on the size of these batches, how these graphs are formed, etc. You should think of it as the worst case instance. There is an oblivious adversary that is picking these batches and how they are connected to the offline set. All right. So what we are going to do is coming up with a multi-stage fractional matching algorithm. Basically, at every stage k, once the batch uk arrives and you get to see the edges ek, you want to pick a point x in 0, 1 to the power ek, a feasible matching for that stage, so that basically you satisfy the matching constraints on the online side and on the offline side. Meaning that every online node should be matched to at most one offline node, that's the first constraint. And then defining yj to be the consumption level or the matching degree of each offline node at the beginning of the batch k, you want to have a consumption that is at most 1 minus yj on each offline node. This is a feasible matching. Yes, Paul.
So all these problems, certainly that the graph, the adversary picks is oblivious, it's not adaptive, but the patchy, can it be adaptively played?
Imagine the entire instance is picked by an oblivious adversary, which means how the online nodes are divided between the batches of the
Probably the batching being adaptive doesn't screw us the same way the graph being adaptive to.
It's not completely well-defined thing. What does that mean? Because
No, but the graph is still designed, right? The adversary fixes the graph. Then, like online, you can fill in with the decisions. Okay, so now so far, this is how you match.
So K is a fixed number, so the adversary cannot play with the number of patches.
Correct, but in this batch, it can. There's no what happened so far. I can decide what to put in this batch.
So let's say you have K equal to 2, and the adversary can be adaptive. Then again, you will face into this issue that you cannot get better than half competitive because the second batch is basically just the second vertex. And if the adversary can decide on that subgraph, that means the adversary can decide on the edge. So an adaptive adversary can exclude you exactly the same way that excludes you non-match.
The graph is still the same, right? It's still like it's just what you're putting into each batch that it's not like because I know the C graph that you're talking about. Those things cannot happen here.
Yeah, but let's take it up front. But I see what you're saying. Yeah, I haven't thought about it like that. Basically, what I'm thinking about is really
So the
this
graph
worst
is for
case
sure fixed.
instance of my
Right. If that if you change, surely you cannot beat half. After that, like
good question. Right, so the goal is to maximize the total weight of the matching at the end, and you're trying to be as close as possible to the optimum in hindsight benchmark, the maximum weight matching. All right, so yes.
So the yj depends on, at time k depends on all your systems.
Exactly.
And do you know what y0 is for all?
Let's say 0. So there is no allocation at the beginning.
Okay.
So basically, at the beginning of the game, when before the first stage arrives, all the yj's are 0. And then you make allocation decisions. Then you have to update by yj. You go to second stage. Right. So we need to first find a metric to quantify different algorithms in this setting. As you probably have guessed, I'm going to look at the notion of competitive ratio. So what does competitive ratio mean? Let me define this number gamma k to be the best competitive ratio that can be achieved by a multi-stage algorithm. And what does that mean? So fix the multi-stage fraction algorithm, like the one that I showed you earlier. I'm looking at the expected weight of the algorithm divided by the weight of the optimal offline solution. And then I'm looking at the worst case quantity you can get among all the problem instances that you might have. So that will be the competitive ratio of that particular algorithm, and gamma k is simply the best competitive ratio you can get using a fractional algorithm. K is the number of stages.
So number of batches?
Number of batches. Okay. Think of k equal to 3, you have 3 stages. Correct. If k equal to 1, kind of related to Nagin's question, so gamma k is going to be equal to 1. This is the optimum of that. If k is equal to the number of online nodes, and also add this assumption that batch sizes are equal to 1, this is going to be the fully online node. So basically, gamma k is going to be the whatever you can get in online matching when you have k number of arrivals. All right. And the question is really what would happen in this middle ground regime when k is greater than 1. And let me tell you what you can do, for example. First of all, any greedy algorithm, any greedy allocation algorithm is going to be half competitive. What does the greedy algorithm in this context mean? At every stage, just find the maximum weighted matching given the remaining capacities on the offline. And if you concatenate these matchings together, you're going to end up with a half competitive algorithm. This is fairly easy to show. But in fact, you can easily do better than that. Why? Because you can just pretend that the batch has arrived in an online fashion. Even though you have these batch arrivals, just pick some arbitrary ordering over vertices in one batch and run an online algorithm on this instance. And for this particular problem, vertex weighted B matching, there is a variant of the balanced algorithm that is going to be 1 minus 1 over E competitive. And let me spend 10 seconds to tell you what does this algorithm do. Imagine a new online vertex arrives. So this algorithm is going to continuously and fractionally allocate infinitesimal amount of resource to the offline node that maximizes this quantity, wj times 1 minus e to the power yj minus 1. So you should really think of it as a a score that you give to each offline vertex, which is a combination of weight and the current consumption level. And then after allocating dx amount, it's going to update the yj's and continuously do that until you get to the end. And as it turns out, this is going to be the optimal competitive algorithm in the online. There are several other works that think about multi-stage combinatorial optimization. Sahil has a beautiful paper who is sitting in the audience, thinking about the edge arrival version. None of them is directly related to this, so I don't want to go through them, but I would be happy to chat about how some of other works might give you alternative algorithms. None of them is going to be able to beat 1-1. Yes.
I have a question. Given that I see the batch and I see all the edges, why wouldn't I just pick the offline optimal matching for that batch, right? Because
That's the degree algorithm.
I see. Okay, got it.
That's the degree algorithm. That picks the maximum weight matching in the current subgraph given the remaining capacity, and that gives you half complex.
Got it. Okay.
You need some sort of hedging, and this is basically the essence of this talk. How to do the hedging. Yes, sir.
Just make sure like the weights are on the offline vertices, not the online one.
Correct. The weights are on the offline. All right. So now I can define my formal research question. In the middle ground regime with k, let's say, strictly greater or equal than 1 batches, what's going to be the optimal competitive ratio that can be achieved by a fractional algorithm? And here is the main result. So we basically show the matching upper lower bounds. So gamma k is going to be equal to this quantity, 1 minus 1 minus 1 over k to the power of k. So the result consists of a lower bound and an upper bound. On the upper bound side, basically show there is an instance. It's actually using the batching structure, such that no online algorithm, whether fractional or integral, can do better than 1 minus 1 minus 1 over k to the power k in terms of competitive ratio. And then we have kind of a interpretable simple algorithm that can obtain this competitive ratio. Let me dig a little bit deeper into this number. So if k is equal to 2, you get 3/4 approximation. If k is equal to 3, you get 19 over 27. This is strictly larger than 1 minus 1 over e. As long as you have constant in many batches, you obtain constant improvement over the number 1 minus 1 over e. It converges to 1 minus 1 over e from above as k goes to infinity. This becomes basically 1 minus 1 over e, and somehow suggesting that the benefit of the batching exponentially degrades as the number of batches grow. I would say this might be an artifact of worst case analysis, and maybe with other forms of input instances and arrivals, you might be able to get different interpretations. But one thing I want to point out, my understanding of what's happening here is basically if you have an algorithm and you let the algorithm to have look ahead, maybe by looking at k stages in future, then even with constant look ahead, you are going to get constant improvement over what you could get in the optimal plan. Yes.
Suppose that I'm in the Uber selling, right? So I get like in a city, I'm getting like 5,000 customers per day. So even if I like delay my things like by 10 minutes, I'm gonna still k is gonna be in the order of 1,000.
Yeah.
Then that's the case, then k could be like posting.
This work actually started when I was consulting Uber back in 2019. And there, what they wanted to do, I think I can reveal to some extent because it was joint work with Amin, and Amin revealed that 2 days ago in a portion, so it should be kosher to me. So, yeah, that's true. Fair enough. So there, basically, they really wanted to incorporate just one iter feature. Let's say there's just one stage coming after. So there's some riders that they have already accepted their price codes. And then there are some riders that they have opened up, but they haven't accepted the price codes. So you have this set of candidate riders, but it's not yet finalized. And the question is, how do they make the matching decision for the current batch, given this uncertainty about the second batch?
No, I understand the
and
problem is
that's how you should really fit this particular result to the right chain.
No, but my point is that if I think about your result is that it just showed this result shows that like for the Uber case, actually doing this batching is not that helpful because for those cases k goes to infinity and you just go back to 1 minus 1 over.
I mean, it depends on how you define the horizon, right? So for example,
it's more like, I guess you're saying it's more like you would be doing the only local allocation. In some sense, you're dividing it into two.
Two, yeah. So let's say I just want to see the effect of one look ahead versus green, right? So you want to understand how much one look ahead is going to help
So
you.
you are just, okay, so you're limiting the horizon and you're saying that you are in the K equals to 7.
Yeah. And in fact, actually, even with that one look ahead, you can see huge improvements when you run these algorithms in practice. I can tell you a little bit offline.
And what can you say about the sizes of the batches?
It's flexible. It can be anything. So the only parameter of the problem instance that we care about is K. It should be fixed. So I'm tying the hands of the adversary on that front. But whatever the adversary puts into the batch is flexible.
So the encompasses both, like saying you have like very small batches and large batches as well as ones.
Yeah, exactly. Daniel?
I actually, sorry, I have a related question. Like, it seems like K and T, like K and the horizon are intimately related. And that's not entirely clear here to me because.
Yeah, so T is going to be greater or equal than K, and that's the only assumption.
So isn't K then sort of a meaningless quantity by itself?
I'm not sure because
if you're in the sense of like if you're batching on a minute by minute level, then like per hour you're batching 60 times, but per day you're batching 1440 times.
Right, but then the question is why are you competing with the best in high-tech solution for the day? Because that might be too good of a benchmark to achieve. So maybe you're better off to just like look at a heuristic and try to see if I add K look ahead, how much I can get improvement over that heuristic. And that's basically what we showed you in some sense.
I think the way I think is T is meaningless.
I think T is meaningless. Why should I care? Because it's an infinite horizon problem, really.
Well, they should be the horizon for you to get new cars in the system, right? Because they have this fixed supply, so these should be sort of like a renewal of that.
Sure. At the same time, I would say that you should not use this matching for long-term horizon. You should really think of it as a local decision making. So let's say in the next 30 seconds, I want to improve the matching algorithm. And then I'm saying, okay, so there will be probably like 3 batches here. Earlier, I was ignoring the effect of the second and third batch on what I'm going to do in the first batch. Now I'm going to improve upon that and see what this. But really, this doesn't fit completely well in the ride-sharing application. However, in video ads, I would say this is actually pretty good in the sense that there maybe in the 10 minutes I'm just gonna try to see how much improvement I get. Some of the ads are going to be shown as minute 5 and minute 6. So there you might end up with 4 batches, 5 batches, and in the next 10 minutes I try to make the matching decision as optimized as possible using this thing.
The lower bound. The batches have equal size or it's some
No,
bounds?
they don't.
Don't.
Yeah, and therefore this lower one doesn't apply to online matching.
That probably relates to my question. I was going to ask if I said K equal to T, I should get online matching out of this.
Correct.
But your lower bound is bigger than 1 + 1 over E, which is
Because great question. So when they say in online matching, the lower bound is 1 + 1 over E, the worst case instance actually has infinite maintenance. Because adversary can.
So what you're saying is if you have finite number of nodes,
then you can
the lower bound
get
is actually
it's slightly better on 1 - 1 over E, but there is just a tiny bit of improvement.
Yeah. So and if this maybe an open question like whether this bound is achievable using integral matching.
Yeah, that's one of the open problems. Great. For K equal to 2, we can achieve 3/4, but for K even equal to 3, I don't know how to get 3. Still 9/10. Right. Cool. So as Sahil pointed out, we are looking at fractional matching, and we can actually extend this result to vertex-weighted B matching when you have capacities not equal to 1, and budgeted allocation, assortment, etc. And the same results can be extended to the integral allocation when you have large budgets. We have a recent paper which is focusing on video advertisement allocation in applications such as YouTube. And there, what we really do is solving the multi-stage configuration allocation. I'm going to spend a few minutes, if time permits, at the end of my talk, talking about that variation as well. Cool. So how much time? Okay, I have. It's great to have a talk over there. So besides the number you saw in the previous slide, I personally am excited about this series of work because of this new algorithmic idea that introduced the literature. And that is kind of using convex programming to make allocation decisions in online algorithms. And in particular, what we are proposing is using what I call a regularized convex programming allocation, and in particular, a polynomial regularized convex programming allocation to solve this problem. So what we basically do in this paper is we identify a unique sequence of polynomials of decreasing degree, where the polynomial with the largest degree appears in the first stage, the second largest appears in the second stage, so on and so forth. And then we these polynomials to regularize the greedy algorithm, the LP that you can write for max weight matching, the one that you pointed out, to introduce a structured balances in our allocation. And then the interesting part is, because we are using convex programming, you can actually use convex duality to decompose the graph that you have in every stage into some sort of decomposition. And then we use the graph decomposition in order to set up a linear programming-based primal-dual analysis to get the bound. So basically, the paper is kind of making this connection between convex programming and online algorithms on the design of the algorithm side. And also we use the convex duality in order to come up with a primal-dual analysis for the LP that you have, the LP for the maximum weighted match. You have to sit in my talk. Yes, that's the remaining half of my talk. Great. All right, so the rest of the talk, I'm going to show you how we can design this kind of balanced allocations using convex programming. And then I'm going to touch the
question. Like, if I assume each batch was of size 1, would it then, like the algorithm that like water filling sound, give me this result?
You should also wait.
Okay.
I have it on one of my slides. Okay. Cool. Yeah, and then if time permits, I'm going to show you how to analyze this algorithm using the graph decomposition. I try to scratch the surface a little bit and give some of the high level. Let me start by some simple examples. In particular, I'm going to start with this very simple example when I have 2 stages. There are 4 offline nodes. There are 4 online nodes. 2 arrive at the first stage. And imagine there is a complete graph between the first stage batch and the offline. The adversary is going to shoot you 2 edges in the second stage. You don't know which of the 2 offline nodes is going to pick by the adversary. So maybe the best thing you can do is really having a fully balanced allocation by picking a fractional matching that uses every offline node with fractional degree equal to half. And that gives you the competitive ratio of 3/4. So here it seems, balancedness is going to be helpful to obtain meaningful algorithms. Here are 2 questions. Do I always want to pick a maximum weight matching or maximum matching in first stage? And the second question is, do I always want to have a fully balanced allocation in the first stage? So let's see the answer to this question. So for example, on this example, I have 2 nodes. The weight of the first node is W plus epsilon. The weight of the second node is W. If I go with the maximum vertex weighted matching, I'm going to always allocate the online node to this guy. So therefore, the adversary can screw me very easily by shooting this edge. Therefore, this algorithm only gets half. But in fact, if you again do the balanced allocation, you can get competitive ratio of 3/4. Do I always want to be balanced? Let's see another example. I have W1, W2. W1 is much larger than W2. This time, I'm going to go with the balanced allocation. Again, the competitive ratio is not going to be more than half because you're losing half of the potential of your allocation. But it turns out that with really careful allocations on these 2 online nodes, you can obtain the competitive ratio of 3/4 again. In fact, all you need to do is to allocate proportional to the weight. So if the allocation on the first guy is W1 divided by W1 plus W2, and the remaining is on the second guy, then you can show that you are going to end up with a competitive ratio of 3/4. So from these examples, I hope I could convince you that you need to do hedging to be robust against an adversary that is designing the second stage and third stage, so on and so forth. But at the same time, you want to have a structured hedging that incorporates the graph that is revealed at every stage together with the weights on the offline side, so that you can use all the information that you have in your best. And at the same time, the fact that there will be some number of edges, some number of stages that will be remained throughout the horizon. So here are a couple of questions. How can I formalize the notion of balanced matching when you have a general graph? And how can I impose it by an algorithm, and how can I analyze that? So I'm going to hit the two birds with one stone by answering both of these questions through the same thing. And that brings us to regularization, which is really a systematic approach to incorporate balances. What I'm going to do is I'm going to use a strict convex regularizers in the objective of the grid algorithm to incorporate regularization. So when I tell you exactly what's the algorithm that uses regularization, I actually wanted to point out that you see regularization all over the place across different corners of computer science, operations, and economics for different purposes. But somehow the fundamental reason behind all of them is the same thing. For example, in supervised learning, we use regularization to avoid overfitting, which is some sort of robustness against misspecifications in data. In economics, you use, again, regularization to have fairness in allocation, to have balancedness. In finance, for diversification of portfolios. Even in online learning, we saw in the previous workshop that you can use regularization to have online learning algorithms that are robust to adversarial attacks. And even in mechanism design, regularization will help you to make algorithms robust to misspecifications in types, the report of the types. And these techniques, some of these techniques can be used to transform algorithms into Bayesian incentive compatible mechanisms. I have a paper on that Balu mentioned. I wanted to point out that this is a very interesting concept, and it appears in several corners. I think regularization in general needs to be more studied and better understood. So the way I'm going to use it in my talk is the following. Just as a recap of the notation, UK is a set of vertices arrive at the stage K, EK is a set of edges. And now I'm going to set up the LP for maximum weighted matching that you saw in previous slides by adding this regularization term. Let me open this term. We basically have a summation over all offline nodes where each term is weighted with WJ. And then we have this function f of k. We should really think of it as an integral of a monotone increasing function little f that as its input gets the final allocation level of offline vertex j. And then the rest is the polytope that you have for fractional matching in a stage K. So you set up this convex program, and then you can solve it. For example, you can use the exponential function, convex polynomials, negative entropy as choices for function capital F of K. And let me actually show you one choice that answers Ola's question and reinvent an existing build in the literature. As a reminder, this is a balance algorithm. Now, look at the special case of our problem where you have basically batches of size 1, only one vertex arrive at a time. And suppose I'm looking at the regularized max weight matching when my regularizer is basically the integral of the function e to the power z minus 1. All right? And I'm using the same regularizer term at all the stages. Now, if you carefully look at the convex program and take the gradient with respect to the variable yj, the final water level of each offline node, then you notice that the gradient is basically this function wj times 1 minus e to the power yj minus 1. All right, so if I give you a convex program and you want to solve it, what would you do? You run a first order method. One first order method we can run is coordinate ascent, which is the following. So you calculate the gradient, you find the coordinates that has the maximum improvement, and you move a little bit along that coordinate. So the balance algorithm is basically coordinate ascent when you run it on this convex program. That answers your question. So there is this deep connection. But here's a catch. This algorithm is using the same regularizer at every stage. And now let's think about it. If we start from the last stage, do you really want to do any hedging? The obvious answer is no, because in the last stage, you just want to pick the maximum weight matching given what you have done in the previous stages. Now you go one stage earlier, you know one stage is coming, so probably you want to have more balancedness in your allocation, you want to increase the amount of hedging. And now we go to two stages earlier, two stages are going to come after me. So again, you want to increase the hedging, so on and so forth. So somehow you want to have an algorithm design technique that increases the amount of hedging as you go to earlier stages.
So
yes.
Always like the maximum weight matching, it's just that you wanted to spread it out. Like
no, so if you have uniform weights, what you're saying is correct. But if you have vertex weights, you are not always picking the maximum weight of matching. Basic distribution of the convex program is going to always give you a maximum matching if your weights are equal.
Yes.
That's the way it is.
Because by just perturbing the ways, the unique maximum is like, there's a unique maximum and it's very much.
Right. So here's the question: how can you increase the hedging effect of a regularized?
Sorry for following up. Yeah. So then, if I have an unweighted setting, I might not necessarily need to change the hedging.
Well, so that gives you a way to find a proper distribution over integral matching. And changing the hedging is changing that distribution. I mean, changing the regularized, changing that distribution.
Do you need to do that? So, do you need to do that?
I do.
Uniform weight.
Yes. For two stages, you don't. But for k stages, you actually need different distributions of different. Yes, sir.
So with the hedging being the most at the top, this is like, okay, this is the highest degree polynomial, which is the hedging.
Answer my question.
Oh, okay.
Yeah, so to increase the hedging effect of a regulator, all you need to do is to increase the degree of the polynomial. And this is, so basically, the one way to think about it is, as you have a polynomial of larger degree, somehow you have more aggressive term in your objective, and that introduces more hedging. And in fact, this is what we see also as we design this algorithm. So what I'm going to do is using these polynomials and change their degrees as I go to later stages in order to decrease the amount of hedging. And I have these polynomials. Imagine the following polynomial, a little f of k at a stage k is going to be 1 minus 1 minus x divided by k minus k to the power k minus k. So this is a function that converges to e to the power x minus 1 from below. And now capital F is just going to be the integral of this function, and I'm going to use these regularizers in my algorithm. So if you're wondering where they're coming from, they are actually coming from a recursive backward functional equation. And this recursive backward functional equation is something that came out of our analysis framework. And then the initial point is the last stage. I already knew the solution for the last stage, so we don't need any regularization term. So the function should be constant 0. And then by plugging that and solving this, you get this sequence of polynomials. And we believe this is actually a unique solution. This is the unique solution for this recursive equation. I kind of think this is actually a unique algorithm that gives you the right complexity direction.
In practice, you want to use this. So first, I need to use like set k for myself. For example, say like k is going to be 3, and then move forward. And then as I'm like increasing k, other for example, I don't consider a bigger benchmark for myself, right? Because as you said, k is equal to that gives me like one step looking at k equal 3 gives me.
What does the benchmark even mean?
Meaning that like you are going to compete yourself against like the optimal offline within this like window that you have like feedback.
Sure.
So if you are going with from k equal 3 to k equal 4, so then you are considering you want to be good compared to
because
offline across this like 40. So
you're making your benchmark stronger.
Yeah.
Then and therefore it feels natural to. Yeah.
But can I like if you have that in mind, can I start the algorithm and say okay?
This is how you use these algorithms in practice. That's what I meant by looking. So you assume I have one looking at.
Right now you said okay, case fix, and then you do this back.
That's for the theoretical analysis. But in practice, when you run these, so if you run it forever, so you want to restart and basically use the one looking at that. And this is exactly what the 2SH algorithm in the Uber application was doing.
So restart.
Yeah. All right, so let's put the pieces together to see the final algorithm. So we are going to solve these convex programs. Function f1 is going to be used in the first stage. That's the polynomial with the degree k. You will have a degree k regularizer in second stage, so on and so forth. And then the last stage, you basically run the grid. You pick the maximum weighted matching in the remaining instance. Yes, Bob.
One point about the previous slide about this uniqueness of this algorithm. Is it true for all online matching things, right? Like ranking is unique.
Let me give you a counter example.
Okay.
So ranking for other bipartite matching gives you 1-1. Butterfilling gives you 1-1. But then there is a hidden fractional algorithm. That's the probability that's created by the ranking algorithm. And those properties are not the same as what butterfilling gives. So I already gave you 2 fractional algorithms for online bipartite matching that gives 1-1.
But 1 is like a limit is, but do they give the right?
No, so the ranking algorithm is 1-1 already on any problem.
But it's a limit as n goes to.
So the worst case for that algorithm is when n goes to infinity and it's gives the 1-1 already. In fact, we can show ranking is a 1 minus 1-1 over n to the power n completely.
But you both algorithms give that.
Oh.
There's only 10 there.
Yeah.
Because somehow I always felt these online matching things are unique, but so I wanted to ask.
Yeah, well, this is a great point. Let's not claim the uniqueness to be on the safe side.
It could be unique. Actually, I do believe it is unique. Actually, I do believe you claim.
Yeah, that's just my hunch. Yeah. Great. Cool. So in the remaining 5 minutes, I try to state some of the main ideas how to analyze these algorithms. So the main analysis technique is just a Primal-dual framework for the linear program of optimum offline. So on the left-hand side, you see the primal, which is the max weight matching on the entire graph. And on the right-hand side, it's a dual LP, which is kind of a vertex color. So you have 1 dual variable alpha I for each online node, 1 dual variable beta j for each offline node. You're minimizing summation of alpha I beta j such that you cover every edge. And covering every edge essentially means that the sum of the duals on that edge should be at least the weight on the offline. The primary solution is going to be the solutions that you get from this capital K number of convex programs. And now, if I can support this solution using a dual that is approximately feasible and has the same objective as the primal, then this is going to be a certification for approximate optimality of the primal. Basically, my goal is to come up with a dual solution such that the change in the primal and change in the dual, the entire primal object and entire dual objects are equal to each other. And my dual is approximately feasible. Basically, alpha I and beta j are non-negative. And for every ij, alpha I plus beta j is at least gamma k times wj. If you have such a certification, then you have a proof for gamma k competitive ratio of your algorithm. And the name of the game is really how to design such a dual. And here we go with the graph decomposition. As it turned out, from the convex program that you have for every stage, you can come up with a particular graph decomposition. Let me tell you what does this graph decomposition look like to answer Nagin's earlier question. This is basically the subgraph that you have in a stage K. Imagine I solve the convex program and I look at all the edges where x star kij is strictly greater than 0. Basically, every single edge that is used somehow by the solution of the convex program. Then we look at the connected components of this subgraph. And these are going to be these pairs that you see on this slide. The moment that you have such a decomposition, then some properties come out. The first property is what I call uniformity. You can actually show for each of these pairs, if you look at any offline node, this quantity, which is the weight times 1 minus little f at the final allocation of that node, is going to be constant among all these nodes. So you can basically assign this number, the uniformity constant, to each of these pairs. The second second property is monotonicity, which basically says that there will be no edge in your actual graph from the online side of a pair to the offline side of another pair if the uniformity constant of this pair is smaller than the uniformity constant of the other pair. And finally, there is this property we call it saturation in the paper, which basically says that all of the online nodes are going to be fully matched in this stage, except everything that is in the last one with the smallest uniformity constant. If you're wondering where is this beast coming from, it actually comes from the KKT condition. So you can really write down the KKT conditions of the convex program, and by playing around with that, you can prove all these properties.
So you're using this condition to come up with a graphic composition?
So we use the KKT, no, so the graphic composition is just this. Find this subgraph and its connected components, and that gives you.
Such that you have this to satisfy this.
And then it will satisfy this property. And how to show that this satisfies this property using the KKT page. This is kind of like magical. You're right. I mean, all I do is I find this subgraph and I then observe these things.
And these properties hold only for the particular regularizer that you chose, or like more generally?
Great. So these properties hold for any convex function that you put here, but definitely you get a the properties hold for any convex function. Right. Yes.
Do you know like a combinatorial algorithm to find out?
Yes. So the unweighted version, when all the vertex weights are equal to each other, is an example of a Galois-Delmos decomposition, which is for general graphs. But if you look at the special case for biproduct graphs, then this is what is known as matching the skeleton. Sahil has a paper that has used the matching the skeleton in different contexts. And it was in this paper of Ashish Goel and others back in 2012. And there is actually a combinatorial way of coming up with the Galois decomposition. Basically, there is a recursive algorithm that finds the most hyper matchable pair first. The decomposition pair has the maximum uniformity, brings that part out, and then recursively continue. For the general convex program, I don't know. I tried it a little bit hard. I didn't actually know that. I was hoping to get the graph decomposition for the general base. I was trying to mimic those algorithms, I couldn't. I ended up saying that actually you can get the properties directly by looking at the feature of the convex program. But this is a great question. If you have any ideas, I would be happy to. All right. And this decomposition gives you all you need in order to have the right dual construction. In particular, I'm going to construct my duals in the following way. Initialize all the alphas and beta j's to be 0. Then when a batch arrives, find the structural decomposition that we saw in the previous slide. Now, for each online node, look at the decomposition pair that the online node belongs to and set alpha I to be the uniformity constant of that pair. And then on the offline side, update the beta j by adding this term delta beta j, which is really the difference between the weight of that offline node and the uniformity constant multiplied by how much allocation that offline vertex got in that stage. For the experts in the audience, this is a high-level generalization of the Primal-dual framework that we have seen for other online bipartite allocation problems, including AdWords and vertex-weighted online matching. So this is kind of extending that Primal-dual framework in a kind of different way to batch arrival when you have multiple number of batches. And to this day, I still have a hard time to really see why convex program was the right way of looking at things and could get us this extension. And I'm still exploring some of the things that you can do with the convex programming. Yes, sure.
Can you simplify you multiply it by the sum of x stars? I guess this gives you like approximate feasibility, but if you didn't multiply by that, you would have like full feasibility.
Correct.
And so
you need that in order to ensure my lemma 1, so that the change in the primal is equal to the change in the dual. The Sherry's point is, why did I update my dual like this? Why this is not 1? Because this is going to be better for dual feasibility. But then you don't want to have a very large dual. In particular, you want to have a dual that's the dual objective is equal to the primal objective. And it turns out that by updating that way, you can ensure at the end of every stage, using the uniformity and saturation, the change in the primal objective and change in the dual objective is equal to each other. And therefore, at the end, the dual objective and primal objective are going to equal to each other. But the main technical demo is showing the dual feasibility. And in fact, what we show is at the end of each stage case, if you look at alpha I plus summation of these delta data from the previous stages, then this is going to already be enough for showing the approximate dual feasibility. And
it's not a IJ case.
That's the solution of the convex program.
No, I mean, this is the optimal for this particular batch.
For batch K, how much allocation you put on edge ij?
Just for this one locally.
Okay, for that subgraph that you observe in stage.
We don't consider the previous thing, just the previous.
Yeah, so there is the information from the early allocation is encoded in YJs, and that's
Yeah,
what
because of the remaining capacity.
yeah. And obviously you don't see the future. Right. But to prove this, you need to use the monotonicity and uniformity. And then there is this induction step that is needed for finishing this proof. From that induction step, the recursive functional equation comes out, and that gives you the polynomials that finishes the out. So I'm really around. We're happy to talk about more details of this proof offline. So hopefully I could convince you something interesting is happening here. I have maybe 1 or 2 more minutes. All right. So let me summarize, and then I'm going to discuss a little bit about 2 papers. So what we saw is basically an algorithm which is based on this idea of regularized max state matching and how this is going to give you the optimal competitive algorithm when you have multiple batches and you're in a multi-stage allocation setting. There are some open problems that come out of this work. Maybe the most important one is something that Sahil mentioned, if I remember correctly, which is the following. Can we show for the integral version of the same problem, the optimal competitive ratio is gamma k? And the challenge is really the challenge that is a rounding challenge in the sense that I have this fractional algorithm that works perfectly. One naive thing to do is independently round it at every stage, but this is not going to work. You really need to correlate the decisions. This is something that we have learned from the entire literature on online matching. And for this particular problem, it's really not clear how to do that. And let me tell you another reason this is a challenging but interesting open problem. If you can come up with another algorithm for this problem, that will give you another algorithm for integral version of online bipartite matching. And to this day, I only know 1 algorithm for that problem, that's ranking. So I have no idea how we can incorporate something like ranking into this convex programming idea and trying to come up with an algorithm. So this seems to be interesting. And my conjecture is, whatever algorithm you come up with should be an algorithm that in the special case, when you have batches of size 1, gives you ranking. Otherwise, you are among one of the maybe top 3 smartest people that I have seen in my life, because many people try to find an alternative algorithm for online bipartite matching and they couldn't.
And this is also unweighted.
Correct. For the weighted version, again, I think there is this algorithm, which is generalization of ranking for vertex weights, that again, I would say in the special case, you should boil down to the algorithm. Okay, and you can think of the stochastic version of the same problem with known and unknown distribution. I think these are a little bit more boring because somehow you can use agreeable de Menor type of result in many of these settings, especially under large budget. Therefore, I'm really interested to know what would be an interesting model that has something new compared to the previous literature. And there are other models that can capture the efficiency between latency and efficiency. They capture the trade-off between the latency and efficiency. I'm curious to know whether there is a legit model in this case. One extension we have is the multi-stage configuration allocation. This is a recent paper. So the idea was in applications such as video advertising, sometimes there are constraints that you would like to have among the ads that you show to the same user that started watching a video. For example, just name a few: frequency capping, the no competitor or diversity constraint. These are really things that people care in practice. If Nike's ad is displayed to a user in one video, you don't want to show the Adidas ad in the same video. And there are many ways that you can incorporate this constraint, but there is a very clean way of incorporating this through what I call a configuration. So you can define a set of configurations that should be assigned to a starting video, and the configuration is going to tell you how many impressions each advertiser is going to get, and what's the price per impression the advertiser should pay. And now the question is, how would you allocate these configurations to video sessions as they arrive? But then because of the reason I told you, there is this natural element for latency. So the question would be, how would you do this in a multi-stage fashion? But as it turns out, the techniques I told you cannot be extended easily there. simply because no graph decomposition exists in that domain. And at the beginning, I thought this cannot be extended. Then we tried hard, and there is a generalization of the regularized convex programming allocation, which I'm going to call it price level regularized convex programming allocation, which essentially do the regularization at every price per impression level and aggregates among all the prices in a smart fashion. And it turns out that gives you the right algorithm for this generalization. And this generalization is rich enough that includes every single online bipartite allocation that I know of. And the second one, we discussed this in the middle of the talk. So basically, you can think about the two stages stochastic matching, where you have some distribution knowledge about the second stage, and now you want to make a decision with an eye towards the future. You can even simulate the future using a simulator, but you don't know the exact realization of the subgraph in the second stage. And now the problem lands in the realm of approximation algorithms. How would you pick a matching in the first stage so that you maximize the expected size of the matching at the end? In the second stage, you always want to pick the maximum matching. So the question is, which matching should you pick in the first stage, given this distribution knowledge you have? So as it turns out, using the distribution knowledge, you can actually do better than the 3/4 approximation algorithm. So we have an algorithm for this problem, which gives you a 1 - 1 over e plus 1 over e squared approximation, 0.78 something. But I think the idea of kind of like using the distribution, competing with the optimum online this time rather than optimum offline, and having improved approximation is something that might be applicable to other problems. And I told you about Yiding. Yiding is going to be on the job market. He was my collaborator in almost all of these papers. The last paper, the two stages stochastic matching, is a collaboration with Yiding and Amin Saberi, who is at Stanford. And with that, I would like to conclude my talk. Thank you so much for your attention. I'm sorry for keeping you from lunch a little bit later. All right.
It's a long pressing question. So let's thank the speaker and